volume fraction of the fiber, let's say 50% volume fraction, so you'll have 50% contribution from density of the fiber and remaining 50% from the density of the matrix, so you can find out the density of the composite. Okay, it's theoretical number. And if volume fraction is, let's say, instead of 50%, it's say 30%, that would be 30% fiber, so 0.3 times rho f plus rho m times 0.7, which is 1 minus 0.3. So that's how you'll find out the density of the composite. So we can also find out density of the composite based on weight fractions. So in the previous slide, this is based on volume fraction. Okay? And in the next slide, we have based on weight fraction. I'll not go into details. This is very basic stuff, exactly like what we did in the previous slide. Just rearrange the terms and you'll get rho c equals 1 over Wf over rho f plus Wm over rho m. So that's how you'll find out the density of the composites if you know the weight fractions. Okay? Very simple. So you can also convert from weight to volume, volume to weight fractions. So if you have if you are working with volume fraction, if you say volume fraction is known, then you can calculate the weight fraction. So that's why I am asking, is your 60% weight by weight or is it by volume? That will make a big difference. You can see that, right? Depending on rho f and rho c, it will make a difference whether it's weight fraction or volume fraction. I'm assuming it's volume fraction, 60% volume fraction. Based on weight, it may be something else. Okay. And if you know the weight fractions, you can convert those to volume fraction. Very simple. Let's say you have multiple fiber types, 3 different fiber types. It is possible. Sometimes you may use, for whatever reason, you may include more than one type of fiber. Okay. In which case, you just use the summation equations. Rho c equals summation I equals 1 to n rho I Vi, where rho I is the density of the ith material, Vi is the volume fraction of the ith material. Similarly, you can use weight fractions. Wi equals rho I over rho c times Vi, and Vi, you can convert them one to other using these expressions. Very, very straightforward. So if you have only 2 items, one fiber and one matrix, one fiber type, one matrix, then this denominator will have 2 terms. Same thing here, just like we had in the previous slide. If we have only fiber and matrix, we'll have 2 terms here. So your summation will be over 2 terms. Okay? So sometimes it's useful to find out the void fraction, volume fraction of the voids. How do you find out? First of all, why do you need that? To find out if your composite is fabricated well, or if it is not made too well, or it's not poorly made, we can figure that out based on void volume of the composite. So V sub V is defined as volume fraction of the voids. So there will be voids in your composite, so that will be your volume fraction of the voids, defined as volume of the voids over total volume of the composite. So that can be found by finding out rho sub Ct. T stands for theoretical. Like if you are calculating the actual rho sub C based on the 2 equations we already talked about, that's your theory. From theory, that's what you get. And if you do a ASTM standard test to find out the actual density of the composite, that would be your rho CE, rho sub CE. C for composite, E for experiment. So rho sub CE. So there will be some difference almost always, invariably, you will see some difference between these two numbers. One is by theory, the other one is by experiments. So you decide or determine the density by experiments and then use this expression to find out the volume fraction. So what do you do with that? Generally it is considered that if the void content is less than 1%, that's a good composite. You have made it really well. If it is greater than 1%, then you can have other problems. So water can penetrate, it will stay in those voids, and if there is freezing and thawing cycles, then you may have some other issues. Okay, so there are many different properties that we will need in our design. Of course, like I said many times, we will not probably, it's highly unlikely that we will as structural engineers design the composites, the actual composites. There are people who are experts in this area. We will let them do their job. They give us a product with mechanical properties clearly specified, and we are going to use those mechanical properties in our structural design. So we have to separate those two. But in any case, we will need, or we hope to have some understanding of the modulus of elasticity in the fiber direction, modulus of elasticity in the direction transverse to the fibers, in plane shear modulus, out of plane shear modulus, and in plane Poisson's ratio. All these items will influence our design. But the supplier will give us all those mechanical properties. That's what we will demand from the supplier, because each and every structural engineer will not have access to determine these properties on their own. So you use their the values supplied by the manufacturer. Okay. So from mechanics of materials, stiffness is defined as based on E. The strain of the composite is change in length delta L over total length. So we will use what's known as rule of mixtures to determine the properties in the longitudinal direction. So if this is our composite, area of the fiber in the whole cross section is A sub F. A sub C is the total area of the composite, and A sub M is the area of the matrix. So those are the three different areas. If there is perfect bond, which is that's what we will assume, there is perfect bond between fiber and matrix. In that case, whatever is the strain in the direction of the fiber, that would be your epsilon C, and that's same as your strain in the fiber, and that should be same as the strain in the matrix. Okay, all three are acting together. There's perfect bond, no slipping. Therefore, the strains in the three items here, epsilon C, epsilon F, and epsilon M, they're all the same. And strain by definition from mechanics is sigma C over EC. Therefore, epsilon C equals sigma C over EC. Sigma C is the stress in the composite as a whole. And then you have strain in the fiber equals sigma F over EF. Strain in the matrix equals sigma M over EM. Very simple stuff. Rearrange these terms, and then sigma F equals EF epsilon F, sigma M equals EM epsilon M. Area of the composite, just by inspection you can see A sub C, the total area of the composite, equals AF plus AM. Therefore, the total force P sub C is equal to PF plus PM. Okay, is that clear to all of you? It's very simple stuff. Is that all right? So now we'll define rule of mixtures. What is rule of mixtures? So based on rules of mixtures, what we will do is, first of all, we know that area of the fiber equals volume of fiber for unit length. So same thing here. AM is somehow related to VM if you consider just unit length of the composite. P equals sigma C times AC, which is equal to sigma F AF plus sigma M AM. Based on this, you have sigma C equals rho f, sigma f times AF over AC plus sigma m AM over AC. Now, considering our volume fraction definition, VF equals AF over A. So, similarly, VM equals AM over A. Now, sigma C from here equals sigma F VF plus sigma M VM. Again, you can say this is based on the strain. So, sigma F equals strain in fiber times EF, that's your stress, sigma F. But remember, strain in fiber is same as epsilon C. I should have it in my previous slide. Okay? So, with perfect bond, remember we said epsilon C equals epsilon F equals epsilon M. Therefore, all these three strains are the same. With that assumption, we have sigma C equals epsilon C times EF VF plus EM VM. So again, you do a little bit of rearrangement of terms. VM plus VF equals 1, and that will give you VM equals 1 minus VF. So I'm just reading these equations, which is quite boring for you and for me, but you have this these slides, so you can easily follow those. So it's very simple stuff. So composite properties can be obtained by adding respective properties of each constituent in proportion to its volume fraction. So from previous slide, we are able to, right from here, we made some rearrangement of terms. We said VM equals 1 minus VF, and based on that, we have EC. EC is what? EC is the modulus of the composite, okay? Equals EF, which is the modulus of elasticity of fiber, times VF is the volume fraction of the fiber, plus EM is the volume fraction of the matrix, and VM is the volume of the matrix. Based on that, we have come up with this rule of mixtures, which is just stating that composite properties are obtained by adding respective properties of each constituent in proportion to its volume fraction. So EC equals EF VF plus EM times 1 minus VF. So we eliminated everything else. We don't have to worry about individual items. All that we need is EF, which you will be known from your manufacturer's data sheets. VF is something you determine. You say, I want 50% fiber volume fraction or 40% fiber volume fraction, whatever it is. So if it is, say, 40% volume fraction, VF will be 0.4. And EM times 1 minus VF is 1 minus 0.4, that will be 0.6. So the modulus of the composite is equal to EC over EM equals EF over EM minus 1 times VF plus 1. So now what we did was, we are just working with proportions, not real numbers. It's only the ratio of modulus of elasticity of two materials. So I can say, let's say I know EM, and I say let my EF over EM, which is a ratio of similar quantities, be 20. So for glass it's likely to be 20. So I plug in 20 here. 20 minus 1 is 19 times VF. Now I don't know what my VF is. I can, if I know EM, I can find out VF. If I want to limit my VF to 50%, I have to use a stronger material and make this simple equation work. That's what it is. Design is that, right? You make some assumptions, make sure those assumptions are valid after the calculations. So if you know one quantity, you can find out the other quantity. If you want to find out E sub C and you know EM, you know VF, and you don't have to know EF, but if you know just the ratio, that's good enough. Times VF will plus 1 will give you E sub C. Okay? Am I speaking too fast? Okay, that's good. All right. So, what do you see from that equation? What you see is, in the direction of the fibers, the properties of the composite are dominated by fiber properties. Does it make sense? Makes perfect sense, because fiber has lot of it has main strength or primary strength only in the direction of the fiber. In the other direction there is no strength. Therefore, the composite will assume the same strength or similar strength in the direction of the fiber, but in the perpendicular direction it will be dominated by matrix properties. Does it make sense? So in the direction of the fiber, the mechanical properties are likely to be or will be dominated by fiber properties. In the perpendicular direction normal to the fiber, the properties are dominated by matrix properties. Very good. That's a very good concept to remember, because in most of our structures, the alignment of the fibers will be in the direction of the stress. That's given. But sometimes you may have interlaminar shear. That means one layer of your composite may want to slide relative to the other layer. That's what is known as interlaminar shear. And that's going to be dominated by, absolutely, matrix. So you already know what it is. Very simple. So it's just common sense with some logic. If you apply all of those, we will be able to design our own composite. We don't have to, but it's good to know how it's designed. So packing, based on packing, VF of 90% is possible. That's what they say, but it's highly unlikely. VF of 90 is very, very high. For protrusion, they use a volume fraction of 45%, 0.45. 45% is quite suitable. For FRP bars, in my view, it is 45 to 50. But if you are able to do 60%, it's great. Maybe it's possible with some additives, I don't know. And beyond 60%, there is a problem. What will be the problem? The problem is the fiber won't be wet in all locations. There will be insufficient matrix or resin to wet the entire surface of all the fibers. You want every single fiber, if possible, to be fully wet, right, on the surface. Then only it will stick to each other and then it will function. What's the main purpose of the matrix? Do you remember from yesterday? Stability is good, but I would like even better one. Yes, resin is wet. When it is wet, it is resin. When it's dry, it's matrix. Yeah. So yeah. But my question is, what is the main function of a matrix? Stiffness is good. I like that. Anything else? Bonding is good, but I'm looking for something else. Confinement is good, because if there is any compressive stress, there will be no micro buckling. Yes, agreed. Anything else? I want to hear from those last 4 benches. Come on, throw something, say something. Doesn't matter. Everyone should be engaged. Yes, thank you. That's the main thing. The main thing is the load transfer. There has to be load transfer between fibers. And if there is no wetting, there is no load transfer. If there is no load transfer, the composite it will fail. Okay, thank you. That's the number one purpose of the matrix. All right. So a simple example. Just plug in some numbers, we'll get some numbers. That's very easy. Okay. So calculate the ratio of longitudinal modulus of a composite when you have the properties of the composite for 10% volume fraction. If my volume fraction is 10%, VF is? No, VF. VF is 0.1. That's right. That's exactly right. 10% means 0.1. Okay? So use not in percentage, but use 0.1. Excellent. Then if it is 45% VF, that means it's 0.4. If it is 75%, it's 0.75. Perfect. So we'll use those fractional values. Okay? Then we have elastic modulus of glass fibers. Let's say 10 MSI. I had everything in MSI units. I added this GPA units so that you can relate to these numbers much easier. So it's about 68.95 GPAs. That's the reason it's not a whole number. This is a whole number, but that's not. 68.95 GPA, carbon fiber, 344.75 GPA, epoxy resin, that's what they are using, some kind of epoxy in those bars. So that's 0.5 MSI. So I just, for those of you who are interested, I just added this conversion factor so you can do the conversion yourself if you want. So the primary thing is we want to find out the modulus of elasticity of the composite. That's what we are going to do. For glass fiber, when we use glass fiber, that's one case. And the other case is when we use carbon fiber. Okay? So, and in each of these two types of fiber, we have 10%, 45%, and 75%. 75% we know is not practical. We know that. But just in case we are able to use 75%, what will be the property? That's what we are trying to do. Okay? Same thing with carbon fiber. 10%, 45%, 75%. So we'll have 6 different sets of results. We should have. Okay? That's what we did here. So, remember I said we are working with ratios rather than absolute values. So EF over EM is 10 over 0.5, which will be same as 68.85 over 3 point something, right? How much was it? Yeah, 3.447. So this is 68.95 over 3.447, the ratio of these two numbers, which will be 10 over 0.5 is 20, right? Very simple to calculate. So that's one ratio. The other ratio is 50 MSI and resin is 0.5, so 50 over 0.5 is 100.